So let's check in here. At this point in our unit of study, you should be able to solve all three of these example problems illustrated here. Number one, if you were given any number of discrete charges, for example, Q1, Q2, and Q3, and the question was find the net force on any one of them, you should be able to apply the superposition principle and Coulomb's law and determine that value. Problem number two is a problem in the motion of a charged object through a uniform electric field, in this case an electron passing through a pair of charged plates, similar to the behavior of a cathode ray tube. So you might have to solve for the angle at which the electron emerges out the other side of the CRT. We should be able to apply the work kinetic energy theorem to determine how far, what distance will a charge travel into a uniform electric field before its motion is reversed. What we need to get into now are some problems in which you have to determine what is the value of the electric field at any point in space around any distribution of charge. And we'll start with the simplest charge arrangement of all, and that of course is just a single monopole. So it always helps to picture what the electric field looks like. So if this is a positively charged monopole, we know the electric field lines are going to radiate outward in all directions. Now there's symmetry to this electric field, but it's not uniform, right? A uniform field has to be of a singular magnitude and singular direction. Okay, so don't confuse symmetry with uniformity. So let's say we have to find what's the value of the electric field right here at this point P. Well, very simple. All we need to know is what's the distance from the center of our point charge to that point P in question, and we label that as lowercase r. Electric field is defined as force per unit charge. So whatever other charge Q I'm going to put here, the force that this charge Q would experience if it was exactly 1 coulomb of charge at that point P, the amount of force per that coulomb of charge is the electric field at this point. But even if I don't put the 1 coulomb charge there still exists the field. So based on Coulomb's law, so if we think of it like this, Q1 is the charge that's creating the field, and Q2 is the charge that's responding to the field, then what we really mean is the electric field is defined as the force experienced on charge number 2 divided by the amount of charge on charge number 2. Of course, it's equivalent to say that Q2 is making the electric field as Q1 is responding. After all, Newton's third law tells us that forces are equal and opposite, so this is a mutual force of repulsion between two positive charges. Anyway, we cancel out the Q2 and we find the electric field is equal to K times Q1 over R squared. In other words, just as we said, the electric field is being created by charge number 1. Of course, we don't really need to put subscripts 1 and 2, because whether there's 2 charges or not, even this one original charge by itself, Q, is creating the electric field. So we say for a point charge we can find electric field just by saying E equals KQ over R squared. Okay, so here's a more challenging problem. What if you had a piece of fur or wool and you rubbed it back and forth across the surface of a plastic rod? So that plastic rod is now uniformly charged. In other words, if we were to slice this up into little bits, maybe we make 1, 2, 3, 4, 5, 6, 7, 8, 9. Would we make 10 or 11? I guess we made 11 little slices there, didn't we? So if the whole rod has a charge Q and an overall length of L, then we can find a density of charge, a linear density of charge. If we want, we can give a symbol to that. Maybe we'll use the Greek letter lambda. Anyway, the linear density of charge should be some number of coulombs per meter. So I can find it just by dividing the total charge by the total length. But the point of saying it's uniformly charged is that if I were to just take this piece right here, now it only represents a little bit of the total charge. So maybe we'll say it has just a small fraction. Maybe we'll say it has an amount of charge dq. In other words, if all of them are the same little bit of length and we lay this rod along the x-axis, then any one of these little pieces has a width that takes up some fraction of length along the x-axis we'll call dx. So the total charge q can be found by just summing up all of the dq's. Every one of them has the same amount of charge as any other because each one is the same length dx. So we're just imagining either taking a bunch of small bits of charge that are nearly like a point charge, right? Any one of these tiny little cylindrical pieces approximates a spherical point charge. And then if I take several of these and link them together, I can build a rod out of it. Or vice versa, we can imagine taking the rod we start with and breaking it into little small bits. The reason we want to do that is because then we can use the superposition principle. The problem might go something like this. Find the electric field at this point P. And maybe we'll label the distance from that point to the left edge of the rod. How about we call that A? So let's make a frame of reference. Put that left end of the rod at the origin. And again, imagine breaking the rod up into several little bits. Each one contains a small fraction of the overall charge. We call that fractional charge dq. And we make note that we can either find that linear charge density by dividing the total charge by the total length, or by dividing that fractional amount of charge by the fractional amount of length that it takes up. So the distance from the point in question P to this one element of charge that I've identified, we could label as R. There'd be a little bit of electric field pointing in this direction due to this small fraction of charge. It's not the total overall electric field at this point, it's just a small contribution to the overall field, so we'll call that dE. Just as well, if I were to take that little element of charge, which also has a value of dq, then the distance from here to here would be a different value of r, so r is a variable quantity. There'd be an even stronger contribution to the electric field from that one just because it's closer. So I would take all of these and add them up, and what I want to do is shrink the size of these slices down so small that they become infinitesimally small, and then I would say the overall electric field isn't just a standard sum by the superposition principle of all the contributions to the overall field. At this point, if we make the slices small enough, then I suppose we'd be integrating to add everything together. So that's the idea. And in fact, either one of these values dE is just going to be k times dq. Okay, so whether it's this dq or this dq, that's the same value, divided by, well, whether it's this r or this r, I need to divide by r squared. So all of the dE's are going to be satisfied by the same expression, but just note that every one of them has a unique value of r. So r becomes the single variable for our calculus. So we make the substitution that E is the integral of k dq over r squared. So like I say, we want r to be the variable, but we notice the element of integration is dq. So we'll take advantage of the uniform charge density to make a substitution just by cross multiplying. if we multiply both sides of this equation by dx, then we can substitute and say dq is the same thing as q over L times dx. Let's call this step 1 of our solution. Step 2, the overall electric field at point P due to this entire distribution of charge across a rod is equal to the integral of K times Q over L dx over R squared. So we still don't have it down to a single variable. R is a variable and X is a variable. So we need to continue to make substitutions to get this down to calculus of a single variable. So this is why it's important to draw a really clearly labeled diagram of the problem at hand. Let's draw this again to be clear. So there's A. Let's just pick any one of our elements of charge. Maybe this one here, we call it dq. So we have no choice about this one. The distance from the origin on an x and y axis to any point in question, we already know must be labeled as x. The distance from the point where we're trying to find the strength of the electric field to the location of the source of charge producing that electric field, we call r. And so it's really clear that r is just equal to a plus x. So step 3, we make another substitution. The electric field that we're solving for is equal to the integral. We can pull some constants out at this point, can't we? So k is a constant, q is a constant, l is a constant. Let's take all those out. So we have k, q over l times the integral of dx over a plus x squared. Now we have it down to calculus of a single variable. A is a constant, x is our variable. And we need to include our limits of integration. So where are we integrating from? From x equals, well, the very first element of charge sits here at x equals 0, and then we have another element of charge here, another one here. We're going to account for every one of them until we get to the last one here at x equals L. So from x equals 0 to x equals L. If we want, we can make a u substitution at this point. Say u equals a plus x, and that means du is equal to dx. And it just changes our limits of integration. So the electric field is kq over L times the integral of du over u squared. And let's see, if x is equal to 0, then u would be equal to a. And if x is equal to L, then u would be equal to a plus L. So you should know the solution to this integral. E is equal to kq over L times negative 1 over u, with limits of integration going from a to a plus L. We could change this to a positive and then flip our limits. So a and a plus L. So the electric field is kq over L times 1 over a minus 1 over a plus L. Let's clean this up and see if we can simplify this. So how about we make a common denominator? The electric field will be kq over L times a plus L over a times a plus L minus a over a times a plus L. So when we combine the numerators, the a will subtract out, and then this L and this remaining L will cancel, and so we get a final result that the electric field at that point is equal to kq over a times a plus L. Box that up, and as a final step, we should check to see if this is a reasonable result. So again, what we're saying is, as long as we have some point that lies along the axis of the rod at any distance, whether we want to find the electric field at this X marks the spot, or here, whichever one. Let's say we pick this. Then we define that quantity as A, and the entire rod has an overall charge of Q and an overall length of L. Then we know the electric field right here at this chosen point is equal to KQ over A times A plus L. But what if we choose to shrink this down and make the rod shorter, but keep the same value of A? How will that change the answer? Well, it's still the same formula that applies here. Let's take the ridiculous case of shrinking the rod down. Let's shrink it down so much that we can approximate it as a point charge. Then wouldn't we expect the electric field right here just to be KQ over A squared? Well, that's exactly what we've done. We've shrunk it as L approaches 0. And if we look at our solution that says E equals KQ over A times A plus L, that's exactly what we get if we let L equal 0, right? This agrees perfectly with Coulomb's law. So it seems like we probably have a valid solution. So in the next few videos, we'll see if we can determine what's the electric field for, well, I'll give you a few ideas. If we took a piece of plastic and bent it into a ring, here we're looking on a three-dimensional axis. We've got the X, Y, and Z axis coming out of the screen, so to speak. So if we rub this plastic ring and give it a uniform charge, and now we want to find what's the electric field maybe at this point P. Or, another example, we might say we take a piece of plastic and bend it into an arc. And if we were to continue that shape, that arc might be a fraction of a circle. The question is, what's the electric field at the center of curvature of this charged arc? What else might we solve for? What if we have a disk? Here we'll rotate it on its side a little bit, so it looks like the previous picture. So instead of a ring, this is a solid disk. Again, there's the x-axis, the y-axis, and the z-axis. And again, we might want to find the electric field at this point. Okay, so those aren't all the possible cases, but just giving you a preview of some of the other distributions of charge we might solve for. In the end, what we're going to want to do in every one of these cases is imagine breaking the shape down into little incremental bits that just contribute some fraction of the overall charge, capital Q. And then that little bit of charge, whether it's in case number 1 or case number 2, or this case number 3, for example, in case number 2, if we say the whole arc has a charge capital Q, and we find a little element of that charge dq, we picture what would the electric field contribution at the point P look like for that element of charge. Well, it would be a little bit of the overall electric field pointing down and to the right, and according to Coulomb's law, that little bit of the overall electric field could be calculated as K dq over, we call this distance R, so over R squared. And to find the overall electric field, we're going to have to sum up or integrate all the little contributions to the overall field. And then somehow make substitutions to get this all into calculus of a single variable. So there's a preview of things to come. Here's our first example, the uniformly charged rod. And as always, thanks